What's that?
I had a question about
Mhm.
with the piecewise function.
Yeah.
Like from 0 to 3, those separate.
Yeah.
When you complete that, you're supposed to get a pretty ugly function at the end.
It's pretty ugly.
Okay.
Yeah.
I got that and I thought to myself, there's no way this is correct because it's canceling out.
Yeah.
And then that's when I thought to ask you about like, hey, are all these L's supposed to be the same? So,
Yeah.
Yeah, that's a no picture.
Uh-huh.
And it, ironically enough, they all canceled out very nicely.
Yeah.
And I still felt like it was wrong. I said, I don't know.
As long as you showed your work, that's the thing. Yeah. Sometimes they can be really ugly where there's just like nothing canceled out. You have like 11 terms.
Yeah.
But sometimes they cancel out too. But then that also gives you anxiety. It's like, oh, this is a little bit too simple too.
Yeah. Especially when I saw it said one of the first 3 n values, and I saw that there were just 5, 6 terms that weren't canceling out. And they said this would be a very, very long answer. So it's,
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, it's our first lecture this week as we had the midterm obviously earlier this week. So I haven't looked at the midterms at all. I haven't had a chance yet. I'm hoping to probably get to them maybe over the weekend because tomorrow is a bit busy for me. So I'm still hoping to get them back to you guys by Tuesday. But that is a little bit optimistic. And so at the latest, I'll have the exams ready for you guys by next Thursday. I know there's some of you, attend the lectures virtually. And so I'll send an email on Monday if I think I'm going to finish the midterms by Tuesday, so you can come pick it up. And so if it doesn't look like I'm going to finish by Tuesday, I'll send an email to everyone. But then I'll have it done by Thursday for sure. Okay. But yeah, so I'll have that ready for you guys next week. Now that we're done with the second midterm, we've started kind of the final topics in the class here. We're very much, going to start wrapping up this semester. So let me just kind of lay out to you kind of my plan for the rest of the semester. So we have, counting today, we have 5 more class meetings. So we have today, 2 lectures next week, and then 2 lectures during week 16, the final week. I do want to reserve the very last lecture of class of this semester to be just a review session for the final. And so I'm not planning on introducing any new information on that last lecture. We may finish sooner than that, but at the very least, I want that last class session to be a review session. So that means there's 4 more lectures of information that's going to be out there. Okay. There is one more homework assignment as well. So there's a homework assignment associated with these probabilities and statistics stuff that we're going over. I'll probably have that due at the end of week 16. Just so I can post the solutions and have those ready for you guys to study for the final exam as well. Okay. Final exam, I actually need to look it up. I don't remember exactly which day it is. But it's going to be 4 p.m. either on Tuesday or Thursday of finals week. I would need to kind of double check. Usually it's the Tuesday, but I'll double check and send everyone an email once I'm sure. Okay. So for the final exam, the final exam is going to be cumulative. So it is going to cover topics that we've covered all the way up from the beginning, but it's not going to be all comprehensive. So there are going to be topics that I'm going to curate for the final exam. So you don't have to study absolutely everything. And so usually what I tell students is that, the amount of topics that's covered in the final exam is probably around 65–70% of everything that we've covered in class. Okay. All of the probability and stat stuff is going to be on the final just because I haven't had a chance to test you on that. And I'll just kind of tell you what I'm thinking right now. So for the final exam, I'm thinking first order ODEs, Laplace transforms, Fourier transforms, and probability and stats. And so the topics that I'm cutting out are going to be second order ODEs, all the vector calculus stuff, and the Fourier series, just because those have already been kind of featured pretty prominently in the first 2 midterms. Okay. I'll officially put out a study guide next week, just so that you guys know. But I do want to say it verbally so that you don't study absolutely everything. Just because I know you guys have other final exams and projects, and so and it's impossible to cover absolutely everything in one exam anyway. So I want to be kind of straight up and just tell you what I would expect for the exam. Okay. In terms of what you can bring for the final, I'll cover this a lot more the next few weeks too. But since there is going to be more information on the final, I am going to allow you to bring 2 cheat sheets for the final. So that's 2 8.5 by 11 sheets. You can put anything that you want on them as well. Okay, but that's something that we'll go over again, in the coming weeks. But I do want to, since we are kind of starting to wrap up the semester, I at least want to tell you kind of my plans, so we can kind of start to get ready. Okay. Yes, question.
For the conceptual questions, will that include all the topics throughout the semester, or will they stick to what you just told us?
It'll stick to just what I just told you. Yeah. All right, and so topic for today is I think we had just a little bit more to finish up from our lecture last Thursday. So we were we didn't get a chance to talk about the normal distribution, so we'll talk about that today. And that's actually a great segue because then that's going to lead into our discussion of confidence intervals, which is the main topic for discussion for today. Okay. All right. Any questions on just anything we've covered so far? Any questions on the final or just the last few weeks? Okay. All right. So let's go and get started. Okay. So since it's been a while, let's kind of just have a very brief refresher here in terms of what we are looking at. Okay. So the whole theme of this section, the section that's going to take us all the way up until the end of the semester, is probability and statistics. Okay. And so the whole idea with this section is to say that, what you model and what you calculate on pencil and paper, everything we've done up until this point, differential equations, vector calculus, Fourier series, those are all great theoretical things to know, right? But in reality, things don't quite work out. Right? And so in reality, any kind of event or any kind of, measurement or observation that you make is subject to at least some uncertainty. Okay. And that leads to a lot of consequences. But I think the main thing is that, each time that you observe something, each time that you measure something, even something that you've already kind of analyzed and predicted using mathematical equations, every time that you do so, it leads to a slightly different observation. Okay. And so, of course, the example that I keep coming back to, just because it's the easiest to mention, I think it's the one that everyone experiences every day, is your commute time, right? So your commute time is not always exactly the same every day. If you measured it down to the second, you'll see that you probably get a very different answer. Well, maybe not very different, but slightly different answers every single day. Okay. Even if you live on campus, right? Just the path that you take, just walking, from your dorm to the classroom, you're not going to do that in the exact amount of time each day. But sometimes you have to wait for the elevator. Sometimes it's cold, and so you're kind of shivering, or you're walking a bit faster, right? So there's always going to be some degree of uncertainty. And the way that we model this mathematically, right, is we use what's called a random variable. Okay. So random variables are going to be central to kind of basically everything that we're going to be talking about from here until the end of the semester. Okay. So a random variable is one that does not have a fixed value, but every time that you observe it, every time that you measure it, or the term that we typically use is sample it, right? So each time a random variable is sampled, it's subject to have its value change. Okay. Right. So a random variable is perfect for representing things like your commute time, which is going to change every time that you come to school. Right. And so for a random variable, we don't think of random variables in terms of fixed values anymore, right? So we don't say that, the random variable has a value of X, right? Instead, the way that we define a random variable is by its probability density function, by its PDF. So remember, the PDF is a graphical representation in terms of what values you can expect from a random variable, right? So even though random variable is going to have its value be different every time that's measured, it still follows some rules, right? So it's kind of randomness within some bounds, let's say, right? Okay. And depending on the shape of the PDF, right, you can see that maybe some values are preferred more, right? So these certain values will appear more often than some other ones, right? And so probability density functions is a very rich field. There's so many different types of density functions that are out there. We're just going to go over just kind of the very basic ones just because of the time that we have remaining, right? So I think the most one of the most basic PDFs out there is the uniform distribution. So I think this was the example that we did kind of right before we left off last Thursday. Okay. So the way the uniform distribution works, it is basically a square pulse, right? So we have values of t and the probability density function of t, right? Right. So the uniform distribution gets its name because the probability that the value of our random variable, the value that it takes is uniform. So it doesn't prefer a certain value. It can be anything between A and B, right? Anything random there. Okay. But the uniform distribution does have bounds, right? And so the probability of something occurring outside of A and B, so the probability of our variable having a value less than A or greater than B is 0, right? So this does constrain our value, but within those bounds, we do have an even probability. Okay. Okay. And so we took the uniform distribution just because it is mathematically very easy to compute things like the mean and the variance, right? So that's kind of the last thing that we did. All right, so the first, I would say, kind of new piece of information today is we're going to talk about the normal distribution or the Gaussian distribution, and kind of discuss the features of that. Because that one is a very important one to learn as well. In fact, it's going to form the basis of a lot of the theory that we're going to talk about today with respect to confidence intervals and for other stuff that we're going over in the following weeks. Okay. Okay, but that was just a very quick recap in terms of why we're studying this and just a bit more about random variables. Any questions on any of this so far? Okay. All right, so let's get into it then. Okay. So the next distribution that we're going to look at is the normal distribution. Also called the Gaussian distribution. Okay. So this probability density function is attributed to Gauss. That's why it's named after him. Some people pronounce it Gaussian distribution, but I think Gaussian is a little bit easier to say. Okay. Or I would say kind of the informal name for the Gaussian distribution is the bell curve. Which I think a lot of just college students are familiar with because a lot of professors grade on the bell curve. All right, so if you graph it out, it looks like the following. It looks like a bell, hence the name. Okay. Okay, so typically we have our axes just like this. Right, so for a Gaussian distribution, we have, it starts out low, it comes up to a peak, and then it goes back down again, just like that. Okay. All right, so what's unique about the Gaussian distribution is that there is a clear preferred value, right? So wherever the peak is, that's where you're most likely going to find the value of your random variable if you were to sample it. Right, so the location of this peak here, this is our expected value. This is also our mean. Right, so there is a clear favorite. There is a clear value that we expect it to be or expect it to take for a Gaussian distributed random variable. Okay, but there is some spread, right? So that's kind of how we describe it. So there is some spread in possible values, right? And so the spread of a Gaussian random variable depends on the width of this peak. Right, so we can kind of measure this this width right here. You know, it's not an exact location, right? So I didn't draw that exactly, but just the overall width of the peak. This will tell you the variance. Right, so the wider your peak is, the more varied your variables are going to be. The more narrow your peak is, then it's gonna choose certain values, right? Because you know different Gaussian distributions with different variances may look different, right? And so I think it's a little bit hard to appreciate with just one right here. But you can also have another Gaussian distribution that maybe looks like this, right? So maybe it's wider, right? So a Gaussian distribution like this would have a larger variance because it's a wider distribution here, right? You can also have one, you know, that's maybe a lot skinnier, right? So maybe it's one that looks like this, right? So maybe the peak is a lot skinnier, but you know, it does, you know, go up a bit higher. So in that case, the variance would be lower. Okay. So it varies, right? And so it depends on the nature of the random variable and depends on just how much variance that we expect. Okay. Now, what's kind of the biggest feature for a Gaussian distribution is the fact that there is a singular preferred value. Right? And that singular preferred value is just wherever the peak is. Okay. And the Gaussian distribution also does show that we do expect some variance, right? And so we don't expect the Gaussian random variable to have the same value every time, but the probability of sampling a value that's greater than the mean and less than the mean is the same. Okay. So basically the variance is expected evenly both to both values higher and lower than the mean. So the way that we describe that is that the variance is evenly distributed along the mean. Okay, so in other words, you know, equally likely. Okay. So Gaussian random variables, I think when you tell just any person who doesn't have any background in probability and stats, when you think of something that can change every time that you observe it, I think people generally think of the random variable as if it were a Gaussian, right? And so kind of the most popular way that I think people explain variance is they use kind of the plus or minus notation, right? So I think a good way to kind of illustrate this is to think about how engineering measurements are taken. Right. So typically when you make a measurement, right? So, let's say, think back to any of the labs that you've done, right? You recognize that there is some uncertainty, right? Because the measurement device that you're using is not perfect, right? Even a ruler, right? Even if you're doing something simple like measuring the length of your phone, right? There's going to be some uncertainty in that measure. And so the way that we typically do that is we have some preferred value, right? So let's say that we are measuring the length of the phone, right? So let's say it's 6 inches, okay, plus or minus 0.5 inches, right? So this notation, I think, is pretty familiar for most people, right? So you have a value that you measure plus or minus what you think the uncertainty is going to be in that measure, okay? And so this type of kind of description lines up actually perfectly with how we describe a Gaussian random variable, right? Because here we have a preferred value, and we have the associated uncertainty, and the assumption is that the uncertainty occurs evenly both above and below the preferred value. Okay. So from here going forward, most of the random variables that we're going to think about or describe are going to be Gaussian in nature, right? So there's going to be one preferred value, even variance on both sides. Right, and you can apply the exact same, the exact same phenomenon to kind of anything that you measure, anything with uncertainty, right? Right. So when you talk about your commute time, right, you can talk about your commute time as like 30 minutes plus or minus 5 minutes, right? So you expect it to be, that's the average value, and then the variance is kind of plus or minus. Okay. All right. Any questions on the Gaussian distribution? Okay. All right. So before we move on to the next set of lecture notes, I'll give you a little bit of trivia. Okay. So if you remember from last Thursday, we defined a variable called the standard deviation, right? Right. So we said standard deviation sigma is equal to standard deviation is nothing more than just the square root of the variance, right? So sigma squared here is the variance, right? Standard deviation is nice because it's always going to be in the same units as your mean, right? So variance is always a little bit harder to kind of interpret because it's technically mean squared. But if you want to get it back into the same units as your mean, you have standard deviation. Okay? In fact, right, when you have measurements that look like above, right? This notation here, right, saying that we have 6 inches plus or minus 5 inches, notice that both the mean and the uncertainty are in the same units, right? So this kind of makes the assumption, or it's kind of implied that this uncertainty actually represents the standard deviation because it is in the same units as the mean. Okay. Right. So I think generally when people talk about uncertainty, they'll talk about variance, just because I think variance is easier to say than standard deviation. But just remember, variance always has units of mean, whatever the mean is squared. Okay. So if you want to get back into the same units as the mean, you have to take the square root. But standard deviation actually has an additional significance with the Gaussian distribution. Okay. And so the way that the Gaussian distribution is defined, right, we can use the standard deviation to tell us the probabilities of sampling a value that's outside of certain thresholds. Okay. Okay. So what does this mean, right? So remember, for a random variable, any random variable, every time that you observe it, every time that you sample, you're going to get a different value, right? And so for a Gaussian random variable, the probability that you sample something within one standard deviation of the mean is 68%. If you're wondering why that number is so weird, like why 68%, it's actually based on e, the exponential term, right? So e to the first power is like 2.7, something like that. And so if you subtract that from 10, then that gives you something like around there, something like that. Because the way the Gaussian distribution is defined mathematically, it depends on the exponential. Right? So mathematically, the way that we can say this is that the probability that our value for t, our random variable, is less than our mean, right? So mu here is our mean, plus our standard deviation, okay? But also is greater than our mean minus our standard deviation, okay? Is around 68%. Right. So as long as you're, plus you add the standard deviation, you subtract the standard deviation from the mean, right? There's about a 68% probability that you're going to sample something within that range there. Okay. Okay. All right. So visually, it looks something like this. And so you have your bell curve here, right? You have your mean, which is this value here, right? And so one standard deviation away is about maybe just like that. Okay. And so if we were to draw kind of vertical lines like this, right? So the probability that you sample a value of the random variable, there's about a 68% chance that you land within that shaded region. And so that this definition goes further. So, what do we say about, what if we talk about two standard deviations? So if you talk about two standard deviations, there's the probability goes up to 95%. So the probability that your value t is less than mu plus 2 times the standard deviation, but is greater than mu minus 2 times the standard deviation. Okay. This is about 95.5%. Okay, so two standard deviations away would maybe be something like this. Okay. And so at that point, you have kind of most of the distribution kind of within within the shaded area. Okay. So the probability that you land somewhere in that region is about 95.5%. Okay.
That's just that one of them is within that.
Exactly. Yeah. So one sampled random variable. Right? So you're going to sample one. So the reason I bring this up is that, I don't know if people still do this, honestly, maybe some older faculty, but, when I was in college, a lot of professors, they graded on a bell curve. And what they mean is this, right? So the way they determine grades, and of course, they never explained this because they just wanted to keep it a mysterious process. They computed all the grades, they computed the mean, and said, okay, everyone at the mean gets a C. If you're within one standard deviation of the mean, like one standard deviation will be one letter grade. So if you're over one standard deviation above the mean, you get a B. If there's two standard deviations above the mean, then you get an A, right? And then it goes the other way as well. Okay? So that's kind of how they did that. I don't, maybe I'm just younger and I disagree with that, but I don't think that's a good way to judge a class. You get a nice, beautiful distribution every time, but you kind of force it. But then you also kind of create like a competitive environment in your classroom. I've seen people when I was in college offer to like turn in homework for people. This was before the age of Canvas and PDFs, but then they would take someone's homework and then throw it in the garbage so that they could lower the mean and improve their chances of getting a grade in the class, which is not a friendly exchange if I will be honest. But so I hope no one grades like that anymore. I'm sure some of the maybe older faculty do, but I don't think that's a good way to grade. Okay, but I thought I would just mention that this is just mostly trivia. This is not something that's there, but in case you were curious about what the standard deviation is and how it's been used, this is kind of it. Okay. Okay. All right. Any questions on this? Okay. All right. So let's go ahead and move on to the next set of lecture notes. So that kind of closes the chapter on our first set of lecture notes, just intro to probability and stats. Okay. So the next concept that we're going to go over is confidence intervals. Okay, so confidence intervals, I think, is a really good application for probability and stats, because this is something that you apply to every lab class that you do, and it kind of is applied to anything that you observe more times as well. Okay. Okay. So before we, so to kind of lay the groundwork for this, let's kind of remind ourselves the difference between the sample mean and the mean of a random variable, because those things are different. Okay? So the sample mean is the mean that you obtain from taking the average from a bunch of observations. Okay? So it's literally the mean that you obtain from samples. All right, so the formula for this, we usually give it the symbol X bar. Okay? It's simply just the arithmetic mean. So you're going to add up the values of all of your observation, all of your samples, and then divide by the number of samples, right? That's just kind of how we typically compute averages. Okay, so we have 1 divided by n, multiplied by summation, I is equal to 1 to n. Okay. Right, so to get sample mean, you would need a collection of observation, a collection of data, and you just simply take the average of all. Right, so that's typically how we compute averages for the most part. Okay. Whereas the mean of a random variable, actually is something that has no uncertainty, right? So it's something, you can think of this as the expected value of the random variable. Another way to kind of talk about random expected value is that, that is the most likely value that the random variable will take if you were to draw a single sample. Okay. So unlike the sample mean, there is an analytical formula for this, and it does have a fixed value, right? So it has a fixed value for every random variable. It does depend on the probability density function, but we give this a symbol mu, right? And remember, the way that we computed this was integral from minus infinity to infinity, t f of t dt. And so in some sense, the way some people think of the mean of the random variable is that some people think of that as like the true, right? Right, because so the true mean is not dependent on samples. That's just something that's inherent to the random variable itself. Okay. We can take this a step further and to say that, because usually, when you take samples, when you take observations of a random variable, you can think of that as ways to observe, the uncertainty, right? So when you compute the sample mean, you can think of the sample mean as an estimate of the true mean. Because when you take samples, when you take observations, there's uncertainty in that as well, right? So it's uncertain layers of uncertainty on top of each other, right? Which I know kind of is, to think about, it's a bit confusing, but I think there's a very simple way to kind of understand this, right? And so what you're kind of always taught in your lab courses and just kind of in general, the more samples that you take, the more accurate your estimations for the mean is. Okay. All right. So that's just kind of a passive, common sense thing that I think most people kind of understand, right? Like, if I were to ask just one person in this class, tell me, measure my phone for me and tell me how long my phone is, right? But then if I did the same thing and said, let me ask everyone in this class, measure my phone, right? You trust the second one, right? You trust the second one. So the more samples you take, the more observations you do, the more confidence that you have in the value that you obtain. Right? Right. So our first kind of application for probability and stats is to actually quantify this, right? So based on how many samples that you take, right, we can actually put a number, right? We can actually put some values in terms of how confident we are in our measurements of this quantity. And that's really useful to do, right? Because there are going to be, I'll just kind of give you a very simple explanation, right? And so when you get out into kind of the workplace, right? Ideally, let's say that you're analyzing a certain phenomenon, you're doing certain tests on your engineering project or engineering sample, right? The more measurements that you take, the more samples that you do, the more tests you run, obviously the better, right? Because the more experiments you do, the more confident you are in your measurements. But, practically speaking, you're not going to be able to run as many tests as you want because, your company's going to have a limited amount of budget, limited amount of time, limited amount of resources, right? And so you have to kind of make a decision in terms of, how many samples should we take? How many tests should we run in order for us to have a certain level of confidence in our results? Okay. So if you can do that beforehand, right? So you can do that kind of, in the very beginning, because a lot of times, when you have these engineering projects, the budget is kind of set from the beginning, right? And so you have to have some kind of expectation or some kind of, sense of, how much should we budget for these tests, right? And so having a way to quantify confidence and what we expect, that's something that's really, really important. Okay. Okay, so that's kind of the motivation in terms of why or how we're going to go about this. Okay. And so, the idea is that, when you run tests or when you collect observations, you collect your sample mean. There's also sample variance as well, right? So we can also get estimations for the variance, right? How confident are we in this estimation for the mean? And in certain situations, maybe we can say, maybe we should take at least 5, 6, 10 more tests in order for us to have a lot of confidence. Okay. Okay. Any questions on this so far? Okay. All right. So let's talk about or let's define it first. So the confidence interval, the confidence interval tells us the certain the amount of probability. Okay. It quantifies the probability that if we were to take a random sample or a random observation of a random variable, right? So if we were to take an observation of a random variable, just a single observation, right? So let's say that if we were to run a single more tests, right? The confidence interval tells us the probability that the value of that observation falls within a certain range. And so generally for confidence intervals, there's ways to do confidence intervals with other types of random variables, but in general, we're going to assume a Gaussian or normal random variable. Just because Gaussian random variables are the easiest to kind of understand. There's equal variance above and below. Okay. Okay. And so the way that we express confidence intervals is that you kind of have to communicate two things. One, you have to indicate a range, and then you have to indicate your confidence or your probability that your value will fall within that range. Okay. Okay. So for example, when you express a confidence interval, it basically kind of goes something like this, right? So if we take the example that I know I've beaten this one to death, but let's take our example of our commute time, right? So we can say that our commute time, right? We can say that there's a 95% probability that our commute time will range between 20 and 40 minutes. Okay. Right. So that means if I were to measure my commute time tomorrow, well, probably not tomorrow. I usually don't come to campus tomorrow. If I were to measure my commute time on Monday, right, there is a 95% chance that it's going to fall between 20 and 40. Okay. Okay. So one thing about confidence intervals is that generally as your confidence goes up, right? So as the probability of your confidence goes up, your range also increases as well. Okay. Which might seem a little counterintuitive, right? And so, generally, as you expect confidence to go up, then we should narrow, right? But just the way that this is expressed, right? It's kind of the opposite trend, right? And I think if you actually write it out a few times, it actually makes sense, right? So if I were to increase the confidence in my commute time, right? So let's say I go up to 99% confidence, right? Okay. So the range that I'm about to propose, I have a 99% confidence or 99% probability that the value is going to be within this range, right? But that's a higher level of confidence than the previous one, right? Because in the previous statement, we're basically we're giving space, or there's a 5% chance that our commute time is either less than 20 minutes or greater than 40, right? And so if we're leaving even less wiggle room, but now there's only a 1% chance we fall out of this range, then our range also has to increase to kind of account for that, right? And so, maybe a 99% confidence interval might be between 15 and 45 minutes. Okay. So that gives us some additional wiggle room because we're only giving ourselves a 1% chance of being wrong. And then the opposite is true as well. And so if your level of confidence decreases, but then that can also shrink your range. And so let's say we go down to 50%. Now we're giving ourselves a 50% chance to be wrong. And so now we can kind of narrow our range down, right? And so for a 50% confidence interval, maybe we say our commute is between, I don't know, maybe 28 and 32 minutes. So I think this part here is a little bit counterintuitive. So as your confidence goes up, then your range gets wider as well. Okay. Okay, but that's typically how we express it, and that's kind of the and then next we're going to find out how we actually compute these things. But before we get there, any questions on this so far? Okay, all right. So let's talk about how do we actually compute this. And so the formula we actually use to compute the confidence interval depends on what we know about the random event that we are measuring. So there's basically, in reality, there's lots of different ways that you compute this, a lot of different formulas for a lot of different scenarios, different types of random variables. But for our specific case, for a Gaussian random variable, okay, we're going to first look at the case where we know the variance, and by nature, we can also know the standard deviation. We know that before we take the samples. So the first case that we're going to look at is, let's say that we know the exact value of the standard deviation of our random event. Right. And so in other words, there's no need for us to compute the standard deviation. There's no need for us to compute the variance. We'll talk about, some actual practical scenarios where this happens. This kind of seems like a unicorn type of situation, but there are situations where this is known. Okay. And so the way we compute confidence interval is the following, right? So the first thing we compute is actually quite simple. Okay? So we're going to compute a variable called k, right? So k actually here is going to be the width of our range, or I guess the half range, you can say, is equal to c multiplied by sigma, right? So sigma here is our known standard deviation. I'll define what c is in a second. And then we're going to divide by square root of n, okay? Where n here is the number of samples that we've taken. Right, so you can see our confidence goes, our confidence interval, the more samples we take, our confidence range gets smaller. Okay, so this k here is our confidence range. Okay. All right, and so all that leaves is c, right? So c here is what we call, or what I kind of default, our confidence coefficient. Okay? And its value will depend on the value of confidence that we want to assign to our interval. Okay, so there is a table for this, and this table here is very important. If you read the lecture notes, this table kind of just looks like an afterthought, but you know, it's kind of the main table that we use to compute these. Okay. So the value of C, you know, depends on our confidence. And so, you know, the way that this is computed, or the way that we use it, is we have this table. Okay. So this gamma here, I know I'm kind of throwing a lot of different variables, a lot of different symbols at you, but this gamma here is our selected value of confidence. And so depending on what we choose for the confidence that we want to have, and that is something that you can choose, that's going to change the value of C that we plug in. Okay. Okay. So this table here, I have, you know, there's 4 different values of confidence. And so we have a 90% confidence. Okay, so that's a confidence value of 0.9. We have a 95% confidence, that's 0.95. We have a 99% confidence, so that's 0.99. And then we have a 99.9% confidence. And so that's 0.999. Okay. So the values for C in these situations. So for the 90% confidence, C is 1.645. For 95% confidence, we have 1.960. For 99% confidence, C is 2.576. And then for 99.9% confidence, C is 3.291. Okay. And so once you've chosen for a value for C and you computed K, your confidence interval is the following. Okay. So our confidence interval is to say that our value for T, okay, our random variable, is between, is going to be less than or equal to T bar, which is our sample mean, plus K, which is greater than or equal to T bar minus K. Right, so that kind of fits with the descriptions that we have above. So, you know, depending on our level of confidence, right? So let's say we chose 95% confidence, then we say that we have 95% confidence that our next value for T, the next value for a random variable, is going to be between T bar plus K and T bar minus K. Okay, good. All right, so this seems like a lot of variables here. It seems like it's a bit complicated, but you'll see the calculations are actually quite simple. Okay. Right. So the probability and stats stuff, I kind of save it to the end of the class because you know I know kind of everyone's kind of tired by the end of the semester. So computationally, there's not as much to do. We're not doing just really long integration by parts anymore. The calculations are quite simple usually. It's just the concepts I think are a little bit new and terminologies. Okay. All right. Any questions on this before we jump into an example? Yes.
Sounds like it just kind of computes into a shaded area between 2 bounds.
Exactly.
Okay.
Exactly. Yes, that's exactly what it is. Okay. All right. So let's do an example to kind of illustrate this. Okay. So for this example, let's say I just ask 10 random people in this room, and thankfully there are at least 10 people. Sometimes when I teach this class, there's less than 10 people in the class because everyone's on Zoom. Thankfully, there's 10 people here. I'm not going to ask you to do it, but let's say I ask 10 people in the room to measure the length of my phone. Okay, but the ruler I gave you looks like this. Okay? It goes on, but the main thing is that there's no tick marks in between. So there's no tick mark for half an inch, 1.5, 2.5. There, you only have tick marks for the whole values for the inches. Okay. All right, and so based on the 10 measurements that we're going to obtain, and I'll give you those 10 measurements in a second, we can use that information to compute the 95% confidence interval. Okay. All right, so let me give you the measurements. Okay, so the measurements are the following. Because remember, we can't have any decimal values here, just because the ruler I gave you only has the whole numbers, right? And so even though visually we may see, it looks like the phone is maybe halfway up these tick marks, right? We can only go based on the precision of our measurement device. Okay, so these are the 10 measurements that we obtained. So let's see. So we have 8, 7, 7, 7, 8, 7, 8, 7, 8, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Okay. Right. And so we only have whole numbers here because we're limited by the precision of our measurement device.
So there is a limiting factor that you cannot estimate in between.
Exactly. Yeah. Yeah. I mean, visually, if you have some, I think people just mentally say like, oh, it looks like 7.5, but realistically, when you have measurement devices, you can only go based on the precision. Yeah. And that's pretty realistic too, right? So when you're measuring things in reality, right, you always have to be aware of the precision of whatever device you're using to perform that measure. Okay. Now it's never going to be this ridiculous, right? There's no ruler out there that doesn't have quarter inch, half inch, things like that. But this is kind of a contrived example in that sense. But that is something you always have to be aware of. And a lot of times, a lot of the uncertainty in the things that you measure is driven by that uncertainty in the precision. Okay. All right. So if we want to compute the 95% confidence interval, first thing we're going to need to do is compute the sample mean. Okay. Because that is something that we're going to use, right? And so the sample mean, we'll call it X bar. Okay. We're just going to sum up all of these quantities here and divide by the number of measurements, which is 10. Right? So we're going to take 1 divided by 10, multiplied by 8 plus 7 plus 7 plus 7 plus 8 plus 7 plus 8 plus 7 plus 8 plus 8. Okay. Just taking up all those measurements, just adding them together, divide by 10. So we can punch those into a calculator and compute its values. Although if you are a little bit savvy, and you might have noticed this already, that there's exactly 5 measurements for 7 and 5 measurements for 8. And so we take the average between them, we end up something just in the middle, which is 7.5. Okay. So this 7.5 here, we can say this is our estimate for the true length of the phone. All right, but how confident are we in this? And also, how much do we expect it to vary? Okay, so to compute our confidence interval, we are going to just use our formula that's straight up here, right? And so we're going to compute K is equal to C multiplied by sigma divided by square root of N. Okay, so we can plug in a couple of these values just straight away, right? So N we know is 10, so we can just kind of plug that in just right there. For C, we have something that we can plug in here as well, right? So because we know that we're taking the 95% confidence interval, right? That means our value for gamma here is 0.95. And so the value of C that we're going to use is 1.96. Okay. So the C here is 1.96 based on our confidence level. Okay. Now, what about sigma? Okay, so sigma, that is our standard deviation. It is, yes. But remember, the reason we're doing this example here is we're assuming that we already know the standard deviation, right? So one way we can compute the standard deviation, we can do it based on the samples, right? So we can just compute the variance from these samples and get a variance that way, right? So that is one way we can do it. But for this case, we already kind of know, or we're assuming that we know what the standard deviation is, okay? So a situation like this is actually a very textbook case where we would know the standard deviation beforehand, and it's the reason why I kind of contrived this example, okay? So for this particular example, right, our measurements, or the precision of our measurements, or I would say the values of our measurements, were limited by the precision of the measurement device, okay? And so for situations like this where, our uncertainty is governed purely based on the precision of the measurement, right? There's no other random events that's occurring, right? My phone is not randomly growing bigger or smaller, right? The only amount of uncertainty that we have is just based purely on the measurement device. And so in this situation, the standard deviation, we can plug in our precision of the measurement device. Okay, so for this case, since our ruler here has only 1 inch tick marks, right? At most, we're going to be off by half an inch. Okay. Right? Because if our measurement, or if our measurement was off by more than half an inch, then we would see that in the ruler. Okay. Okay, so we plug all those values in, right? So we plug in 1.96 for C, we plug in 0.5 for the standard deviation, we plug in 10 for the number of measurements, okay? We get K is equal to 0.31 inches. Okay. And so if we take this information along with our sample mean, we can now express our confidence interval, right? Because our confidence interval is to say that the true length of our phone, right, is less than or equal to our sample mean plus k greater than or equal to our sample mean minus k, okay? Okay, and so we put this all together, we can say that we are 95% confident that the true length of our phone is, okay, is between x bar minus k, and so that is 7.5 minus 0.31, so that's 7.19 inches, okay? Less than or equal to the length, which is less than or equal to x bar plus k, so that's 7.5 plus 0.31, which is 7.81 inches. Okay. All right. Any questions on that? Yes, yes.
Just with the how you came up with the standard deviation, is the 0.5 just because it's the middle of the two possible?
Exactly. Yeah. So you can think of that standard deviation as kind of our uncertainty and what we measure, right? And so for a ruler, it looks like this, right, where we only have just whole number tick marks. What we say that and let's say that we measure something and it's like something, it comes up to like maybe right here, right? So it's kind of between 3 and 4 in the case. And so, I think if it's like that, I think most people would say 3. But then, if we say 3, we can say we're rounding down, and the maximum amount that we round down is 0.5. Because if it's right in the middle, right? If it's right in the middle between 3 and 4, we have to choose one. Like we can't say 3.5. And so if it's, we can say 3, but then we're off by 0.5. So that's the most that we'd be off. Because we're saying, if it's greater than 3.5, we'd probably round up to 4.
I see.
Yeah.
And it's like similar for when it's just like one factor that's determining the randomness of it.
Exactly. Yeah. So this is a very simple case where there's only one source of the randomness. Yeah, good question. All right, any other questions on this result here? All right, one more extension to this before we go, right? So let's say theoretically we asked 90 more people. So we say, we want to know this for sure. So if we got 100 measurements, let's say we're using the same janky ruler that doesn't have quarter-inch, half-inch marks. But let's say that we obtain, our sample mean is exactly the same. Right? So we got the same X bar, right? So we got the same mean, but, because we took 100 measurements and we got the same result, we typically say we're more confident in this, right? And so if we recompute K, okay, so K, remember K depends on the number of measurements. Okay. Right, so our measurement device is the same, so we still have the same sigma. Our C is the same because we're going to use the same 95% confidence interval. The only thing that changes here is the N. Okay, so we have N is equal to 100. That's going to lower our range here. So that means our K here is now going to be 0.098 inches. Okay. That means our 95% confidence interval has shrunk to the following, right? So we have more confidence that our measurement is actually true. Okay. And so in this case, our 95% confidence interval is 7.402, which is less than or equal to the length, which is less than or equal to 7.598. Right, so based on 100 measurements, our confidence grew. And the way our confidence grew is that our range kind of shrunk. So now instead of being from 7.2 to 7.8, now we're between 7.4 and 7.6, which is a much smaller. All right, any questions on this before we wrap it up for the week? Okay, all right, so that's all the time we have for today. So when we come back on Tuesday, we'll talk about cases where we don't know the variance beforehand. So these will be cases where, maybe we have more sources of uncertainty. And we'll see how we deal with that. Okay. All right. So thank you guys for coming this week. I will let you guys know on Monday if I will have the exam graded by Tuesday. If not, by Thursday for sure. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys next week.
Professor?
Yeah.
So in this case, is it safer to think that the standard deviation is more so inferred, strongly inferred, rather than known?
Yes, you could say that. Yeah, I think that's probably more accurate way to say that. Because it's something that we are estimating based purely on our measurement. Yeah.
Because I'm assuming when we come on to the standard deviation not being given, we have to do the sigma calculation and so forth.
Yes, so in those cases, we have to compute the sample variance based on our standards. And then, that's gonna replace this standard deviation with the sample line. So then that's gonna change, it's gonna essentially change how we compute the C.
Okay.
Yeah. So we're gonna use a different probability distribution to do this.
Yes, that makes sense. So I was thinking to myself, if it's given, that means someone already calculated the sigma before us.
Exactly.
But otherwise,
Yeah.
just give them what we have.
Right, so for this case, we'll touch on this Tuesday, but for this case, we're assuming that our randomness is purely Gaussian. Yeah, but when you introduce more uncertainty, it could be a different shape. Yeah.
I see where you like this now.
Yeah, it's fun. So it just goes so many layers deep.
Thank
you. Yep.
One question for the course equivalency.
Yeah.
Do I have to submit two forms for the lab and the class, or just
Um,
one form for both?
So you're talking about the circuits.
No, this is for machine.
Oh, machine design, it should just be one, because we just have one, we just
Okay.
have the one 421 here.
So do I just put the main class, because I have to
Yeah,
take both the. okay.
Exactly, yeah, so when you fill it out, just say that this is both courses at Cal Poly Pomona, these are both equivalent to 420.
Okay.
Yeah.
So I put both of the classes in the.
Exactly. Yep.
Okay, thank you.
Yep,